We now look at conservation of momentum problem. This is quite an interesting problem, as you can see from the diagram. According to the question, it says the thrust developed to propel the jet ski shown in figure 2 below is a result of water pumped through the jet ski and exiting as an high-speed water jet. So a certain quantity of water goes in, and through continuity there is a smaller area here compared to the larger inlet area, and there is an expulsion of the water at a higher velocity. Because of the change in momentum, there will be a momentum created in the water towards the right, and the water acts on the ski jet in an equal and opposite direction. So we need to understand the theory first before we plunge to the question. You are asked to calculate the flow rate needed to produce 1,334 Newton thrust. That is 1.334 Newton thrust. Now, question B is the same question, but we are asked to make an assumption that if the velocity at inlet is significantly smaller than the velocity at the outlet, what is the flow rate required? In other words, we are saying that the inlet velocity is very small and can be ignored. So let's get on with the problem. If we look at the diagram, you can see that the velocity at the inlet is an angle 30 degrees to the horizontal. The control volume, of which this is just a sketch of the ski jet, this portion relevant to us, shows an outlet velocity V out. Now, through mass conservation, m dot in must be equal to m dot out. So using the continuity relation expanded and noticing that the density does not change significantly, we can get an expression for the inlet velocity in terms of the outlet velocity and the ratio of the two areas, outlet area over the inlet area. It is good at this stage to pause for some time to look at what it means. If you have an inlet area very much larger than the outlet area, then this expression becomes very small. So in the second part, we are going to use this fact to simplify our calculations. Now, the conservation of momentum equation, at first looks a bit scary, but it's our old friend, the momentum force, Fx, is equal to the mass flow rate multiplied by the velocity leaving in the x direction over the velocity entering in the x direction. So what we have next is we have the outlet and the inlet resolved along the x direction, and this results in our expression here. Now, we know the area, we can calculate the area at the outlet because we are given the diameter. of the outlet jet, and if we continue and faithfully go through the derivation, okay, doing a bit of substitution. I know it looks a bit horrendous, but basically this expression here is just a factorization and a simplification of our terms. And if we go through this carefully on our own, we end up with the mass flow rate, making the mass flow rate the subject of a formula equal to this expression. Now, if we plug in all the terms that we have, we will get our answer of 111 kilograms per second. Now, many of you might be a bit concerned about the second part, but in fact, you can see that the second part will simplify considerably our expression. If V in is very much smaller than V out, I must say at this stage, there was a typo in the question. Okay, so please change the expression that I've circled. V in is considerably smaller than V out. The error in the original question was the V in is very smaller than V in, which is clearly ridiculous. Okay, now if V in is smaller, how does it help us? Let's go back to our formula, and you can see that V in becoming smaller allows us to eliminate this completely. This completely off. This expression completely off on the right. And if we follow through, all these become insignificant. So in fact, I haven't done it and left it in an exercise for you. We don't have to worry about this on the right. Just evaluate the following. And if we have done this carefully, we would get the new flow rate of 91 kilograms per second. This ends the question. Thank you.